Welcome you all for the complex variable tutorial class. In this class, we will discuss about the complex variable. Here, I will start with some basic definition I discussed in the previous classes. Here, we start with let us start with consider an equation x square minus 4 is equal to 0. The solution for this above equation is very easy to compute as 2 and minus 2. That means 2 and minus 2 are the numbers which satisfies the equation 1. When the studies were going on, they come across an equation of the form x square plus 4 is equal to 0, then for which no real number satisfies this equation 2. Since no real number satisfies this kind of equation, they introduced the concept of complex number. The solution is given by x square is equal to minus 4, x is equal to root of minus 4, then this can be interpreted or written as root of minus 1 and root 4. You know that root 4 is a real number, you get 2, that is plus or minus 2. Then root of minus 1 is put it as I, where I is equal to root of minus 1, then using this concept, a complex number is discussed. A complex number is of the form z is equal to a plus ib, where a comma b belongs to R. These things we already discussed in my starting class. Here you can see in a xy plane, that is a Cartesian plane. In this we can discuss in a real plane system. Here in a complex plane, we can make it as real axis. This is an imaginary axis. Here we can put in an ordered pair, that is 3, 4 can be represented as 3 here and 4 in the imaginary axis. 3 is in the real axis and 4 in the imaginary axis. This is depicted in this Argand plane, that is a complex plane. That's why this is the variable we discussed. Z bar, if it is z is equal to x plus I by, z bar is known as the complex conjugate of z. You can see in this diagram the real line, and this is an imaginary axis, and here z is equal to x comma y. That is an ordered pair, or we can written as in a real as well as imaginary. Then it can be put it in a first axis, that is first plane, that is z is equal to x plus iy. It is in the x plus plus will be denoted here. This is minus plus, minus comma plus, here minus minus, here plus comma minus. Then here if it is z is equal to here, then its z bar can be denoted by x minus iy. That is the conjugate. Z is equal to x plus iy, then conjugate can be represented in this way in a pictorial representation. A complex function in a polar form, that is z is equal to r e power I theta, and its conjugate is z bar, here r into e power minus I theta. And also we can discuss in a function of a complex variable. A function w which can be expressed in terms of z is called a function of a complex variable. That is w is equal to f of z, then that is u of x comma y plus I into v of x comma y. Here u and v are the functions of x and y, and w is a function of z, that is z in terms of u plus iv, that is u and v. For example, we can take, let w is equal to z square, then w is equal to x plus I y square, means that is a plus ib the whole square form. Then a plus ib the whole square means a square plus b square plus 2ab. Then here this can be written as x square plus 2 into x into iy plus iy the whole square. If you simplify this, then this becomes x square plus 2iyxy, and I squared is represented as minus 1. That's why here we can written as minus y square. Here this is, you can see that this is x square minus y square is the real function and 2xy is an imaginary. That is imaginary. Here u is be represented as real axis and v is in the imaginary part. That is u real part is x square minus y square and v is equal to imaginary, or v is a imaginary part. And e power ix, these are some of the important formulas we already discussed in the first class. Here we will recall e power ix is cos x plus I sin x, e power minus ix is cos x minus I sin x. And here cos ix can be represented in the exponential function, that is e power x plus e power minus x by 2. This is cos, that is hyperbolic function, that is cos hx, that is the representation of cos hx. Sin ix can be represented as I into e power x minus e power minus x by 2. Then that is I sin hx means hyperbolic function. And also we discussed about the de Moivre's theorem, that is cos theta plus I sin theta to the power of n, that is equal to cos n theta plus I sin n theta. Limit of a function. If complex function w is equal to f of z is said to be tends to a limit w naught as z approaches to z naught, if for every epsilon greater than 0 we can find a delta greater than 0, that is delta positive, such that here mod f of z minus w naught is less than epsilon for all mod z minus z naught is less than delta. This is symbolically, we can write it as limit of z tending to z naught, f of z is equal to w naught. Continuity of a function. A complex function w is equal to f of z is said to be continuous at the point z naught if f of z naught is well defined, and also we have limit of z tending to z naught, f of z is equal to f of z naught. A function f of z is said to be continuous if it does not have any breaks in a given interval. Differentiability. A single valued complex function w is equal to f of z of a complex variable z is equal to x plus iy is said to be differentiable if the limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z is equal to f dash z exists and has the same limit for all the different ways in which delta z tends to 0. And also we know that any function is differentiable means definitely it is continuous. A function f of z is said to be differentiable if we can draw a tangent at each and every point of in the given interval. And derivative of w is equal to f of z is given by, because w is equal to u plus iv, then dw by dz is dou u by dou x plus I times dou v by dou x, that can be represented as ux plus I times vx, because u and v are the functions of x and y. Neighborhood of a function. A neighborhood of a point z naught in the complex plane is the set of all points z such that mod z minus z naught is less than delta, where delta is a small positive real number. Geometrically, mod z minus z naught is equal to mod x plus iy minus x. Here z naught is the x naught plus iy naught, and z is equal to x plus iy. Then we can simplify as mod x minus, because real part can be, we can separate this, that is x minus x naught plus I times y minus y naught. Then if you take, this is a modulus will be there, then modulus of number, that is root of x minus x naught the whole square plus y minus y naught the whole square. Since mod z minus z naught is less than delta, means inside the disk, then we can write this is equal to delta, then this is x minus x naught the whole square plus y minus y naught the whole square is to delta square, means it is a equation of a circle which represent a circle with center at x naught comma y naught and the radius is delta. Now we will discuss about the analytic function. You know that first we discussed about the continuity, next we will discuss about the differentiability, now we will go to inside, that is analytic function. A complex valued function f of z is said to be analytic in a region or a domain if it has a derivative at every point of a region R. Note that if analytic functions are also called as holomorphic function, sometimes we call that as regular functions. And you know that if you discuss about the analyticity of a function, means each and every point in a region is differential. It is very difficult task. That's why the Cauchy and Riemann discussed about the one of the that analyticity can be checked using Cauchy-Riemann equation. That is the theorem. We already proved this one in our previous classes. That is theorem. Again, we will recall here. The necessary and sufficient condition for the function w is equal to f of z u of x comma y plus I into v of x comma y to be analytic. First, the first order partial derivatives ux, uy, vx and vy are continuous functions of x and y. And also it satisfies ux is equal to vy and vx is equal to minus uy. This is the theorem statement of a Cauchy-Riemann equation. Let us consider that the function w is to be analytic. Analytic means it is differentiable. Then derivative exists and is unique, and f dash z is equal to limit of delta z tends to 0 f of z plus delta z minus f of z divided by delta z exists. If this delta z increments of z are increasing to z, then delta x and delta y will also increments of x and y are increments. That is increment or increase. Since z is a function of xy, means definitely delta xz is increment, means delta x and delta y is also increments of respectively x and y. Using the above expression, we will change that u to u and v function here. This is function of z, here u of x comma y plus I into v of x comma y. Here x changes to x plus delta y changes to y plus delta y. Similarly, you get this equation. Then this says if you make f dash z is equal to limit of separate real and imaginary parts here. U is a real parts here u, and this is the uth term you can separate, and here denominator part. And also delta z, you know that z is equal to x plus iy, then delta z is equal to delta x plus I times delta y. The increment in z results in increments of x and y also, that is delta z is equal to delta x plus I times delta y. Then we will get two cases, that is one of them is delta x and another one is delta y. Using the partial derivative definition, we can use this dou u by dou x is equal to limit of delta x tends to 0 u of x plus delta x comma y minus u of x comma y divided by delta x. This is the definition of partial derivative. Let us start with the imaginary changes, that is delta y tends to 0, then delta x does z become delta x, and delta z tends to 0 and delta x is tending to 0. Therefore, equation 2 become f dash z is equal to here x plus delta x comma y minus u comma x comma y divided by delta x plus I into limit of delta x tends to 0, because the plus delta y term becomes 0 in the here as well as here. Then observing this is the definition of the first order partial derivative with respect to u with respect to x, here v with respect to x. Then this become f dash z become dou u by dou x plus I times dou v by dou x. Similarly, we can do the second case. If delta x tends to 0, then the delta z become I times delta y, and delta z tends to 0, delta y tending to 0 means the equation 2 becomes here f dash z is equal to the delta x term becomes 0. Here also delta x is in the denominator, delta x plus that is 0. Here also 0. Then the remaining is this one. You know that any complex number cannot be present in the denominator. That's why first we will take 1 by I as a common factor here. That is 1 by I means conjugate can be multiplied. I conjugate is minus I into I is minus I square minus 1, minus into minus become plus, then the numerator become minus 1 here. Then these I become cancelled. Then this is the definition of a partial derivative of y with respect to partial derivative with respect to u with respect to y here. Both here partial derivative of v with respect to y. Then f dash z become here minus I into this one. Here we can substitute. Then that is minus I dou u by dou y plus dou v by dou y. Here you know that equation 3 and equation 4, both left hand sides are same. Then right hand sides are also equal. Then you know that dou u by dou x plus I times dou v by dou x is equal to dou v by dou y minus I times dou u by dou y. Then here you know that any two complex numbers are equal means real part is equal to the real part of the other and imaginary part is equal to the imaginary part of the other one. Then if you're separating this, you get dou u by dou x is equal to dou v by dou y, dou v by dou x is equal to dou v by dou x is equal to minus dou u by dou y. These are the Cauchy-Riemann equations in Cartesian form. Now we will discuss about the Cauchy-Riemann equation in polar form. You know that u and v are the function of r and theta is the polar form of a complex number. The necessary and sufficient condition for the function w is equal to f of z. U and v are the functions of r and theta. To be analytic, then the first order partial derivative with respect to r and theta, both are continuous with respect to r and theta. Then this condition is satisfied. That is, ur is equal to 1 by r v theta and vr is equal to minus 1 by r u theta are to be satisfied. Exactly similar procedure if you adopt to the what we done in the Cartesian form. Here also you get the proof for this Cauchy-Riemann equations in polar form. Derivative of w is equal to f of z is given by dw by dz, dou u by dou x plus I times dou v by dou x, that is the representation is ux plus I times vx. In polar form, we can make dw by d theta is e power minus I theta ur plus I into vr. Now we will go to some examples related to analyticity and its derivative. Show that f of z is equal to z square is analytic. Also find its derivative. First we can substitute z is equal to x plus iy. Then that become f of z is equal to x plus iy the whole square. Expand this, that is x plus iy the whole square is x square minus y square plus 2i into xy. Here f of z is equal to u plus iv means u is equal to x square minus y square, 2v is equal to 2xy. After separation you get this one. Then by Cauchy-Riemann equation, partial derivative with respect to x here, that is ux is equal to dou u by dou x. Here partially we differentiate with respect to x means x square become 2x and y square becomes 0. Similarly, v is equal to 2xy. Vx is equal to, that is partial derivative with respect to x, that is dou v by dou x. Here x become 1, you get 2y. Then partially differentiate with respect to y here. Then x square treated as a constant, that becomes 0. Y square become minus 2y. B of here partial derivative with respect to y means vy is equal to dou v by dou y is equal to 2x. Here if you observe, ux is equal to vy and vx is equal to uy minus uy. Then this is the Cauchy-Riemann equations are satisfied here. The function is analytic. Derivative of f of z means you know that dw by dz is equal to ux plus I times vx. You already known here ux is equal to 2x and vx is equal to 2y. Substitute here, that is dw by dz is equal to 2x plus I times 2y. Then take 2 as a common factor. You know that x plus iy is z. That is the representation. Means z square derivative is 2z. It is a simple example of the derivative with respect to a polynomial function. Now we will show that in a polar form for same. By substituting z is equal to r e power I theta, then r e power I theta the whole square, r square e power 2 I theta. Then this become, you know that e power ix is cos x plus I sin x by Euler's formula. Here this function become f of z is equal to r square into cos 2 theta plus I sin 2 theta. Then this become r square cos 2 theta plus I into r sin 2 theta. If f of z is equal to u plus iv, then separate real and imaginary part. Then you get u is equal to r square cos 2 theta, v is equal to r square sin 2 theta. Now we will discuss the Cauchy-Riemann equation in polar form. Means partially differentiate with respect to r. ur become, here r square is there, that become 2r cos 2 theta, because cos 2 theta is treated as a constant because we are doing a partial derivative. Similarly, here we differentiating partially with respect to theta means u theta means r treated as a constant. Then you can take as it is cos 2 theta derivative is minus sin 2 theta, and 2 theta can be differentiated, you get 2 here, that is minus r square 2 sin 2 theta. Exactly similar way, v can be differentiated partially with respect to r, then that become dou v by dou r square become 2r and sine 2 theta you can take as it is. Here v is given with respect to theta. If you differentiate, v theta become r square as a constant. Sine 2 theta can be differentiated, that become cos 2 theta, and 2 theta again it is a chain, that is 2 you get, that is 2 cos 2 theta. That is v theta is equal to r square 2 cos 2 theta. Hence, Cauchy-Riemann equation, you know that in a polar form, ur is equal to 1 by r v theta. And Vr is equal to minus 1 by r u theta. If you substituting and rearrange, that is r square r become cancelled, both left hands. If you substituting and check it out, you get a r sine 2 cos 2 theta is equal to r cos 2 theta. Left and right hand sides are both are equal. Then we say that hence the Cauchy-Riemann equations are satisfied and also it is an analytic function. The derivative is given by, the derivative can be differentiated, that is f dash z is equal to dw by dz, that is equal to e power minus I theta, that is ur plus I times vr. Then ur can be substituted, then u power r is equal to, the derivative is given by f dash z is equal to dw by dz e power minus I theta into ur plus ivr. Here ur and vr of the partial derivative with respect to r we already find. Here you can use this ur and vr and substitute. Here then ur is equal to 2r cos 2 theta plus vr is 2r sin 2 theta. Here we can take common factor 2r e power minus I theta, then that is 2 into r into e power minus I theta, this is e power 2i theta. Then you know that a power m into a power n is equal to a power m plus n. Here also e power minus I theta plus 2i theta means you get e power I theta, that is 2 into r e power I theta is 2 side. You get, if you do done by Cartesian form as well as polar form, you get a same result. If you observing the problem, the problems is in the quotient form, then you can use polar form. If you have in a polynomial expression, use Cartesian form. It is useful. I will give one more example related to the analytic and its derivative. Prove that the function f of z is ln z is analytic and find its derivative. Here, logarithmic function always it is better if you put the polar form. Z is equal to r e power I theta, then f of z is equal to ln of r e power I theta. You know that logarithmic function, that is ln r plus I theta. That is log of m into n is log m plus n, and log m power n is log n log m, and log m to base m is equal to 1. Using this condition, we can express this log ln of r e power I theta is ln r plus I theta. Then here the separate f of z is equal to u plus iv means u is equal to ln r and I theta, theta v is equal to theta. Then here you can differentiate partially with respect to r, you get 1 by r, and v r is equal to, here r term is absent, then that becomes 0, and u theta become 0, and v theta is equal to 1. Then using the condition, hence by Cauchy-Riemann equation, ur is equal to 1 by r dou v by dou theta, and dou v by dou r is equal to minus 1 by r dou u by d theta are satisfied, and the function is analytic. Then the derivative is given by f dash z is equal to dw by dz e power minus I theta ur plus ibr is the standard fundamental theorem of calculus. Using that one, then you get 1 by r e power minus I theta. Here, that is 1 by r e power I theta can be taken in the denominator, then that become 1 by z. The derivative of ln z is 1 by z. Now we will go to exponential function problem. Show that f of z is e power z is analytic and also find its derivative. By substituting z is equal to x plus iy, then the problem becomes f of z is equal to e power z, e power x plus iy. E power x plus iy means e power m plus n form, e power m into e power n, that is e power x into e power iy. Here, e power x plus iy become e power x into e power iy. Then f of z, you know that by Euler's formula, e power iy is cos y plus I sin y, then that is equal to e power x cos y plus e power I into e power x sin y. Then separate real and imaginary part. If you put u plus iv, f of z is equal to u plus iv, u is equal to e power x cos y and v is equal to e power x sin y. Then ux, then we will make a partial derivative with respect to x and y. Here ux is equal to dou u by dou x, e power x is e power x, cos y is treated as a constant, we can take as it is. Here v is equal to e power x sin y. Here partial derivative with respect to x means e power x is e power x and sin y is as it is. Uy means partial derivative with respect to y, that is e power x is treated as a constant, cos y derivative is minus sin y. And vy become, that is e power x is treated as a constant, sin y become cos y. You can see here ux is equal to vy and vx is equal to minus uy. Means it satisfies the Cauchy-Riemann equation. Means it is analytic. Then we find the derivative of the given function using dw is equal to dz ux plus I into vx. Then ux is e power x cos y and vx is equal to e power x sin y. Then substituting here in these two, e power x is a common, take outside, then that remaining is cos y plus I sin y. Then that is e power iy. E power x into e power iy is e power z. Then e power x plus iy is e power z. E power x derivative is e power x only. Now we will discuss about the functions that are not analytic. Here this example shows that the function is not analytic. F of z is equal to z into z bar or sometimes mod z the whole square. Mod z the whole square is z into z bar. Then you can substitute z is equal to x plus iy. Z bar is equal to x minus iy. Means multiplication of these two, you get a plus b into a minus b form. Then f of z is equal to x square plus y square. Then here only real part is present. U is equal to x plus x square plus y square. V is equal to 0. If partial derivative with respect to x means here 2x and here vx is equal to 0 or vy is also 0. Ux is not equal to vy means definitely the function is not analytic because it doesn't satisfy the Cauchy-Riemann equations. These are some of the examples are related to analytic function, show that f of z is equal to 1 by z is analytic, also find its derivative. Show that f of z is equal to z power n is analytic, also find its derivative. Show that f of z is equal to cos z is analytic, also find its derivative. Simply we can see this, we can say that 1 by z is minus 1 by z square, z power n is n, z power n derivative is n into z to the power of n minus 1. Cos z is sin z minus sin z. You can do it yourself. We will discuss some more problems in the next coming classes. Thank you.